Hello everyone, welcome to solve this nice math Olympiad exponential equation problem. And here we have 1 to the power of n equals to 2, and here we solve this problem for the values of n. So the very first step we are going to do is here first we solve this into direct method, or we check that is this equation have real roots or not. So that now first we take the natural log on both of the sides of this equation, and we write it as log of 1 to the power of n equals to log of 2. And now after that, here we use the nice property of log, and we move this n to the front of this log, and it will be written as n times of log 1 equals to log 2. And now we move this log 1 to the right hand side, and we separate the value of n, so it is equals to log 2 divided by log 1. So here you see that this is log 2. So log 2 gives us the any constant value. So this is any constant number which is in integer form or as well as in decimal form. But this log 1, we know that log 1 equals to 0, so you know that something over 0 becomes infinity. So it gives us this expression cannot gives us the real root. So here we write it has no real root. So this shows that our given equation cannot gives us the real root. So now we need to find the complex roots of this equation. So we find those complex roots by using the Euler's identity. So here we just we need the Euler's identity, and we know that about Euler identity, it is written as e to the power of iota theta equals to cos of theta plus iota sine of theta. So this is called the Euler's identity. So now we check this Euler identity, some values of theta, is this Euler identity hold or not. So now first we take our theta equals to 0. So when we take theta equals to 0, so we gives us here e to the power of iota into 0 equals to cos of 0 plus iota sine of 0. So here we know that something multiplied by 0 equals to 0. So something power 0 equals to 1. So e power 0 is 1, and cos 0 is also 1. But sine 0 is equals to 0. So this 1 plus 0 becomes 1. So it means that theta equals to 0 satisfied over this equation. So now we take the general value of theta, which is called here theta equals to 2k pi. So we suppose the value of theta in this form 2k pi. So here our k is equals to 1, 2, 3 and up to so on. So these are some natural numbers. So we suppose this k is any natural number. So now we substitute here this value of theta in this equation, and now we gives us its output in this form e to the power of 2 iota into 2k pi. So this is equals to cos of 2k pi plus iota sine of 2k pi. So this is the our Euler's identity in general form. So now we check this Euler's identity to the values of k equals to 1, 2 and 3, and we check the behavior of this identity. So here first we take our k equals to 1. So when we take k equals to 1, it will be gives us e to the power of iota into 2 pi equals to, when we substitute 1 here, it will be equals to cos 2 pi plus iota sine of 2 pi. So we know that the value of cos 2 pi equals to 1 plus iota into the value of sine 2 pi is 0. So this will be equals to 1. Similarly, we check the behavior of this equation by the value of k equals to 2. So when we substitute k equals to 2 in this equation, so it will be written as e to the power of iota into 2 times of 2 becomes 4k pi equals to cos of when we substitute k equals to 2 here, it will also becomes 4 pi and plus iota of sine 4 pi. So now we need a little bit simplification here, and we know that the value of cos pi is equals to 1 plus iota, and the value of sine 4 pi is 0, because we know that the value of cos pi equals to when our pi is multiplied by an even number. So 2 is even number and 4 is also even number, so this will be gives us the positive 1. If we multiply this pi by odd number, so it will be gives us the negative value minus 1. Okay, so these are even numbers, so here we get the positive 1. Similarly, in sine case, if we multiply even or odd number inside the sign, so it will always gives us the value is 0. So that here we get the value of e to the power of iota 4k pi is equals to 1, because 1 plus 0 iota is also equals to 1. Similarly, we check the behavior of a given identity for k equals to 3. So when we substitute k equals to 3, it will gives us e to the power of iota into 6k pi. It is also equals to 1, and here we just write and up to so on. So it means that if you substitute any value of k, it is also gives us the output is 1. So here we generally write this expression as e to the power of iota into 2k pi is equals to 1. Okay, so we find the value of e to the power of 2k pi. So here, because we move towards our final target, so our target is to find the value of n. So now we take the nth root on both of the sides. So here we take nth root, and it will be written as e to the power of 2k pi and its whole power n equals to 1 to the power of n. So here we are given that the value of 1 to the power of n equals to 2. So we use this value because this is our given question statement. So we substitute this value here, and these are exponent to the exponent, so these are multiplied by each other, and we will get here e to the power of iota into 2k n pi equals to, this is equals to 2. So after that, here we need to take the log on both of the sides. So when we take log, it will be written as log of e to the power of iota into 2k n pi equals to log of 2. And here we use the nice property of log, and we move this exponent to the front of this log, and it will be written as iota into 2k n pi into log of e equals to log of 2. So this log e equals to 1, and we move all the values other than n to the right hand side, and it will be equals to n equals to log of 2, and here we have iota 2k pi, so we write it as 2k pi iota. So these are the complex values of n. So this is the our final answer, and thank you so much for watching this video. Please subscribe to my channel for more exciting videos.